This is module 5 of chapter 2. In this module, we shall discuss about a new kind of interpolation method called spline interpolation method. In previous methods, that means Lagrange interpolation method, Newton's interpolation method, we have constructed a single polynomial of degree n. But in spline interpolation method, we construct a polynomial for each interval. That means, for n plus 1 points, we have n intervals and we have to construct n polynomials of degree either 1 or 2 or 3 and so on. If the degree of the polynomial constructed in each interval is 1, then the polynomial or the corresponding spline is called linear spline. If the degree of polynomial is 2, then the spline is called quadratic spline, and if the degree of the polynomial is 3, then the spline is called the cubic spline. Among these three type of spline, the cubic spline are widely used and used by computer scientists for the image processing, computer graphics and many other areas. Now, we consider cubic spline interpolation method, which is more important than other interpolation method or other spline interpolation method. Here we consider n plus 1 points x I y I equal to 0 to n, where y equal to f x. The value of f x is not explicitly available. A cubic spline is a set of n third degree polynomial and each polynomial is constructed in each interval. Now, the interval are denoted by x I comma x I plus 1. This is obviously a closed interval and I equal to 0 to n minus 1, but the polynomial is to be constructed under certain condition which to be stated in next slide. The cubic spline interpolating polynomial is defined precisely in the following equation. Equation number 1, the function phi x, which is defined as p 0 x, which is defined within the interval x 0 and x 1, and p 0 x is a polynomial of degree 3, and p 1 x is another third degree polynomial which is defined in the second interval x 1 to x 2. P I x is the another polynomial of degree 3, that one is defined in the interval x I comma x I plus 1. The last polynomial p n minus 1 x, which is also a third degree polynomial defined in the last interval x n minus 1 comma x n, where each p I is a polynomial of degree 3, and combining all these cubic polynomials we get the cubic spline for the interval x 0 and x n. The function phi x is called the cubic spline within the interval closed interval x 0 x n if phi x satisfies the following condition. These are the main condition for cubic spline. The first condition is the I minus 1 polynomial and the ith polynomial, their first derivative are equal at the x I, where I equal to 1 to up to n minus 1, and this condition is known as equal slope condition, because the first derivative is involved. So, the condition is known as equal slope condition. And second condition is that the second derivative of the polynomial p I minus 1 and second derivative of the polynomial p I at the point x equal to x I, they are also equal, and this is true for I equal to 1 to n minus 1, and this condition is called the equal curvature condition, because the slope are equal, and if the second derivative are equal, then obviously the curvature must be equal for that particular point. And the third conditions are the condition for interpolating polynomial, that are simple, that are p I x I equal to y I and p I at x I plus 1 equal to y I plus 1. This is true for I equal to 0 to n minus 1. The continuity on slope and the curvature are not defined at the end points x 0 and x n. These conditions are different, and these conditions are to be imposed based on the application of the problems. Now, we denote the interval x I comma x I plus 1 by I plus 1 interval. That means, we say this interval as the I plus 1 interval, and length of this interval denoted by h I plus 1, and which is equal to xi plus 1 minus xi. This represents the length of the interval I plus 1. Now, the cubic spline on the interval I plus 1 be defined by phi x equal to pi x, and which is equal to ai into x minus xi power 3 plus bi into x minus xi power 2 plus ci into x minus xi plus di, and this is the I plus 1 polynomial within the interval xi comma xi plus 1, where ai, bi, ci and di are the unknown, and their values are to be determined by imposing the conditions which are mentioned in the previous slide, the slope condition, curvature condition and the condition for polynomial interpolation. Again, we see that the polynomial pix satisfies or passes through the points xi and xi plus 1. Therefore, when x equal to xi, then we see that phi xi, which is equal to yi equal to di, and all other terms are 0, and this is obtained from equation 5 by substituting x equal to xi. In case of x equal to xi plus 1, from equation 5 we have yi plus 1 equal to ai, x is replaced by xi plus 1, that is why xi plus 1 minus xi whole to the power 3 plus bi xi plus 1 minus xi power 2 plus ci into xi plus 1 minus xi plus di. Since xi plus 1 minus xi is the length of the interval and it is denoted by hi plus 1, therefore, yi plus 1 becomes ai hi plus 1 power 3 plus bi hi plus 1 power 2 plus ci hi plus 1 plus di. So, this is equation number 7. Now, we differentiate the polynomial, the cubic polynomial, which is nothing but the equation number 5 2 times, and get the following equations. The first derivative of phi x is equal to 3 into ai x minus xi power 2 plus 2 bi into x minus xi plus ci. This is obvious. This is the first derivative of phi x, that means the first derivative of pi x also, and the second derivative of phi x equal to 6 ai into x minus xi plus 2 bi. Now, from equation 5 we see that the second derivative of yi equal to second derivative of phi at xi, and which is equal to 2 bi. When x equal to xi, the first term of equation 9 becomes 0, that is why this expression is nothing but 2 bi. Similarly, when x equal to xi plus 1, then the second derivative of y I plus 1 equal to second derivative of phi at x equal to xi plus 1, and this is equal to 6 ai into hi plus 1 plus 2 bi. Now, for simplicity we denote the second derivative of y at I be denoted by mi for all I equal to 0 to n. Thus, we have mi equal to 2 bi and mi plus 1 equal to 6 ai into hi plus 1 plus 2 bi, or bi equal to mi by 2 and ai equal to mi plus 1 minus mi by 6 hi plus 1. So, up to this portion we obtain the value of ai, bi and di in terms of mi, but the mi are not known quantities, these are unknown, these are nothing but the second order derivative of phi x or yx. Using the values of ai, bi and di, the equation 7 that one mentioned in previous slide, that one becomes yi plus 1 equal to mi plus 1 minus mi whole divided by 6 into hi plus 1 into hi plus 1 power 3 plus mi by 2 into hi plus 1 square plus ci hi plus 1 plus yi. After simplification or after rearranging, we get the value of ci, which is equal to yi plus 1 minus yi whole divided by hi plus 1 minus 2 hi plus 1 mi plus hi plus 1 into mi plus 1 whole divided by 6. So, this expression, that means equation 12, gives the value of ci. Therefore, we can say that the values of ai, bi, ci and di are available in terms of the unknown quantities m0, m1 to mn. And to find these values, we use the condition 2 mentioned in first slide. That one is the first derivative of the polynomial pi minus 1 and first derivative of the polynomial pi are equal at the point xi, and I is equal to 1 to n minus 1. So, for this condition we obtain another equation. Now, for the polynomial pix, we have first derivative of pi at xi equal to 3ai into xi minus xi square plus 2bi into xi minus xi plus ci. Note that the first two terms of this expression are 0. So, this is equal to ci. And for the polynomial pi minus 1 at x, we have the first derivative of pi minus 1 at xi equal to 3ai minus 1 into xi minus xi minus 1 power 2 plus 2bi minus 1 into xi minus 1 plus ci minus 1. Now, the values of pi dash at xi and values of pi minus 1 dash at xi are equal as per the condition. Therefore, the equation 13 and 17 are equal. So, from these two equations we get ci equal to 3ai minus 1 into hi square plus 2bi minus 1 into hi plus ci minus 1. So, this equation represents a relation between ai, bi, ci and ci. Now, in this equation we substitute the values of ai minus 1, bi minus 1, ci minus 1 and ci. We get this equation, and after simplification of this equation or after rearranging of this equation, we get equation number 15. So, 15 is hi mi minus 1 plus 2 into hi plus 1 into mi plus hi plus 1 into mi plus 1 equal to 6 whole into yi plus 1 minus yi whole divided by hi plus 1 minus yi minus 1 whole divided by hi for I equal to 1 to n minus 1. So, this is a very important equation for cubic spline interpolation. Now, we use some notation to simplify the above equations. We denote hi by capital AI, and 2 into hi plus 1 plus hi plus 1 equal to capital Bi, and hi plus 1 equal to Ci, and right hand side of the above equations is denoted by capital Di. So, using this notation, the previous equation, equation number 15 reduces to ai into mi minus 1 plus bi into mi plus ci into mi plus 1 equal to di, and this is valid for I equal to 1 to n minus 1. That means, this is a set of n minus 1 equations. That means, we can say that this is a system of tridiagonal equations containing n minus 1 equations and n plus 1 unknown m0, m1 up to mn. So, we have seen that the construction of cubic spline depends on the solution of a system of tridiagonal equations. This equation contains n plus 1 unknowns m0, m1, mn, and it contains n minus 1 equations. That means, to solve this system of equation we need two additional conditions or equations, but these two conditions or equations are available from the different kind of problems or different types of applications. Now, some of the application or some of the special cases are discussed in the next slides. Here we consider some particular cases for cubic spline interpolation. The first case is the natural spline. This is a very simple case. In this case, we assume that the value of m0 equal to 0 and mn equal to 0, and the corresponding spline obtained by assuming this condition is called the natural spline. The another condition is this one: if m0 equal to mn, m1 equal to mn plus 1, y0 equal to yn, y1 equal to yn plus 1 and h1 equal to hn plus 1, then the corresponding spline is called the periodic spline. And if we assume the following conditions, that means m0 equal to m1 minus h1 into m2 minus m1 by h2, mn equal to mn minus 1 plus hn into mn minus 1 minus mn minus 2 by hn minus 1, then the corresponding spline is called the extrapolated spline. Now, we discuss another kind of spline called the clamped cubic spline. In this case, the first order derivative at the initial point x0 and the first order derivative at the end point xn are given. That is, we can write 2 m0 plus m1 equal to 6 by h1 whole into y1 minus y0 by h1 minus y0 dash, and the second equation is mn minus 1 plus 2 into mn equal to 6 by hn whole into yn dash minus yn minus yn minus 1 whole divided by hn, and the spline satisfying this condition is called non-periodic spline or clamped cubic spline. We consider extrapolated spline m0 equal to y0 double dash and mn equal to yn double dash. That means, if the double derivative of y are given at the extreme point, that means at x equal to x0 and x equal to xn, then the corresponding spline is called endpoint curvature adjusted spline. Now, for these different cases, we have different system of tridiagonal equation. First, we consider the case of natural spline. In case of natural spline, m0 equal to mn equal to 0, and the system of tridiagonal equations for the unknown m1, m2 up to mn minus 1 is this one. So, this is a matrix equation, contains n minus 1 equation and contains n minus 1 variables m1 to mn minus 1. So, we can solve this system of equation uniquely. Now, for non-periodic spline, the system of tridiagonal equations are obtained in this slide. By introducing the condition for non-periodic spline, we get 2 m0 plus m1 equal to d0 and mn minus 1 plus 2 mn equal to dn, where d0 and dn are calculated in the following expressions. So, for this case, the system of tridiagonal equations for the unknowns m0, m1 up to mn becomes this system of equations. Here the number of equations is n plus 1 and also the number of unknowns is n plus 1. So, we can solve this system of equation uniquely. Now, I go to extrapolated spline. In this case, the values of m0 and mn are given by the following equations, and the first equation can be rewritten as m1 into a1 plus b1 plus a1 h1 by h2 plus m2 whole into c1 minus a1 into h1 by h2, and this is denoted by d1 and this is nothing but d1, or this equation can be written as m1 b1 dash plus m2 c1 dash equal to d1, where b1 dash and c1 dash are given in the following expressions. Similarly, the second equation is changed to mn minus 2 an minus 1 dash plus mn minus 1 bn minus 1 dash equal to dn minus 1, where an minus 1 dash and bn minus 1 dash are given in the following two equations. So, finally, we have the system of tridiagonal equations for the unknown m1, m2 up to mn minus 1 is this. So, this equation also contains n minus 1 equations and n minus 1 variables. So, after calculating the values of m1, m2 up to mn minus 1, we can determine the values of m0 and mn from equation number 17. Now, in case of endpoint curvature adjusted spline, the values of m0 and mn are given. That means, the corresponding system of tridiagonal equations written below. Here also note that the number of equation is n minus 1 and the number of unknowns is also n minus 1. Therefore, we can solve this system of equation uniquely if the coefficient determinant is non-singular, where d1 dash equal to d1 minus a1 y0 double dash and dn minus 1 dash equal to dn minus 1 minus cn minus 1 yn double dash. These are the known quantities. So, we have seen that if the values of m0 to mn are available, then we can compute the values of ai, bi, ci, di for all I, and finally, we obtain the cubic spline. Now, we illustrate this method, the entire method, by considering one example. For this example, we have two sets of value, one for x that one represented in the table as a first row, and second row represents the values of f x. Now, our problem is to find a cubic spline for this table of values with the end condition second derivative of y is given at the end points minus 1 and 2, and both these values are 0. Since these values are 0, so we can say that the corresponding spline will be a natural spline, and also find the value of f x when x equal to 0.5. So, this is the problem. The first step is we have to construct a cubic spline and then we have to find the value of f x for x equal to 0.5. So, here we have 4 points. So, for these 4 points we have 3 intervals minus 1 0, 0 1 and 1 2, and for each interval a cubic spline is to be constructed. Now, the natural cubic spline for the interval xi comma xi plus 1 is pix equal to ai x minus xi power 3 plus bi x minus xi power 2 plus ci into x minus xi plus di. The values of ai, bi, ci and di are given by the following equations: ai equal to m I plus 1 minus m I whole divided by 6 h I plus 1, bi equal to m I by 2, ci equal to y I plus 1 minus y I whole divided by h I plus 1 minus 2 h I plus 1 into m I plus h I plus 1 into m I plus 1 whole divided by 6. And di is very simple, di equal to y I, and all these coefficient ai, bi, ci, di are to be determined for the values of I equal to 0, 1 and 2, because the number of interval is 3. So, we have to calculate 3 sets of ai, bi, ci and di. But for this case, the values of h1, h2 and h3 all are equal to 1. Now, we have to determine the values of mi, and the values of mi are given by equation 15. This equation is nothing but mi minus 1 plus 4 mi plus mi plus 1 equal to 6 into yi plus 1 minus 2 yi plus yi minus 1, but this equation is valid for I equal to 1 and 2. That means, we have 2 equations, one for I equal to 1 and other for I equal to 2. So, the system of tridiagonal equation is given by, for I equal to 1, first equation is m0 plus 4m1 plus m2, which is equal to 6 into y2 minus 2y1 plus y0, and by using the values of y0, y1 and y2, the right hand side becomes 2.52. And for I equal to 2, the second equation is m1 plus 4m2 plus m3, which is equal to 6 into y3 minus 2y2 plus y1, and this is equal to minus 0.9 by substituting the values of y1, y2 and y3. Here it is given that m0 equal to second derivative of y at the first endpoint minus 1, and this one is equal to 0, and m3 equal to the second derivative of y at the another endpoint, that means at x equal to 2, which is also given as 0. That means, using these two conditions, the above two equation reduces to 4m1 plus m2 equal to 2.52, this one first equation, and second equation becomes m1 plus 4m2 equal to minus 0.9. So, this two is very simple and we can solve this equation by any arbitrary method, and we obtain the solution of this equation as m1 equal to 0.7320 and m2 equal to minus 0.4080. Thus, we obtain all the values of m0, m1, m2 and m3. Now, the values of ai, bi, ci and di are given by this formula. Since the values of m0, m1, m2, m3 are available, so we can calculate a0 equal to m1 minus m0 by 6, which is equal to 0.1220, b0 equal to m0 by 2, this is equal to 0, c0 equal to y1 minus y0 by 1 minus 2m0 plus m1 by 6, and after simplification the value of c0 equal to 0.6980, d0 is equal to y0, which is equal to 1.52. Similarly, we can calculate the value of a1, b1, c1, d1 and a2, b2, c2, d2. So, all the values of the coefficients are available in terms of numerical values. So, now we can construct the cubic spline. Hence, finally, the cubic spline is p0x equal to 0.1220 into x plus 1 power 3 plus 0.6980 into x plus 1 plus 1.52, where minus 1 less than equal to x less than equal to 0. Second cubic spline is, or second cubic polynomial is p1x equal to minus 0.1900 into x cube plus 0.3660 into x square plus 1.0604 into x plus 2.34. This is valid for 0 less than equal to x less than equal to 1, and third polynomial is p2x equal to 0.0680 into x minus 1 power 3 minus 0.2040 into x minus 1 power 2 plus 1.2260 into x minus 1 plus 3.58. This polynomial is valid for 1 less than equal to x less than equal to 2. So, we obtain three polynomials, three cubic polynomials for three intervals. The entire sets of polynomial represents the cubic spline. Now, we have to find the value of f x when x equal to 0.5. Note that x equal to 0.5 belongs to the interval 0 and 1. So, to find the value of f at this point, we have to consider the second polynomial p1x. That means, f of 0.5 is equal to p1 at x equal to 0.5, and after simplification we get p1 at 0.5 equal to 2.9398, correct up to 4 decimal places. Now, let us consider another kind of problem. Here a function f x is given. Our problem is to test whether f x is a cubic spline or not. So, here two expressions are given. That means, the first expression is a cubic polynomial, that one valid for the interval 0 and 1, and second one is also a cubic polynomial and the corresponding interval is 1 to 2. So, to test whether the given function is a cubic spline or not, we consider p0x equal to first expression, that one is 2x cube minus 4.5x square plus 3x plus 5, where 0 less than equal to x less than equal to 1, and the second expression is denoted by p1x, which is equal to minus x cube plus 4.5x square minus 6x plus 8, where 1 less than equal to x less than equal to 2. So, for this case x0 equal to 1, x1 equal to 1 and x2 equal to 2. The function f x will be a cubic spline if the following conditions are satisfied. The first condition is pi at xi equal to f of xi. This is the condition of interpolating polynomial. Second condition is pi at xi plus 1 equal to f of xi plus 1, and these two conditions are valid for I equal to 0 and 1. And the third condition is the equal slope condition, that means the first derivative of p I minus 1 is equal to first derivative of pi at xi, and second derivative of the polynomial pi minus 1 and second derivative of the polynomial pi are equal at x equal to xi, but these two conditions should be satisfied for I equal to 1 only. That means we have to show that first derivative of p0 and first derivative of p1 are equal at x equal to 1, and second derivative of p0 and second derivative of p1 are equal at x equal to 1. So, for this purpose we calculate the first derivative of p0, and which is equal to 6x square minus 9x plus 3, and first derivative of p1x equal to minus 3x square plus 9x minus 6, and second derivative of p0 x equal to 12x minus 9, and second derivative of p1x equal to minus 6x plus 9. Therefore, first derivative of p0 at 1 equal to 0, this is easily obtained, and first derivative of p1 at x equal to 1, this is also 0. That means we can say that p0 dash at x1 equal to p1 dash at x1, one condition is satisfied, and for p0 double derivative at 1 equal to 3 and p1 double derivative at x equal to x1, which is also equal to 3. That means the second derivative of p0 and p1 are equal at x equal to 1. Thus, all the conditions of cubic spline are satisfied by the function f(x), then we can conclude that f(x) is a cubic spline. But for cubic spline interpolation, we can mention some important points. The Lagrange, Newton's and Gaussian interpolation formula, including Stirling, Bessel's, we construct a polynomial of degree n for n plus 1 points, whereas the cubic spline generates a set of n cubic polynomials for each interval. This one is the major difference between the other interpolating polynomial and cubic spline polynomial. The second important point is the computation of an n degree polynomial is a very difficult task. It takes lot of time, whereas it is easy for a cubic spline or cubic polynomial. Thus, in computational point of view, the cubic spline is very useful compared to the other methods. The third point is, with respect to computer storage, the cubic spline needs more space than the other interpolating polynomials. To store a polynomial of degree n with coefficient n plus 1 need n plus 1 units of memory space, but to store a third degree polynomial needs only 4 unit space to store the 4 coefficients. But for a cubic spline there are n polynomials each of degree 3. So, to store the all cubic spline, all n cubic spline, we have to use 4n unit of memory space. Thus, with respect to storage, the other polynomials are better than the cubic spline polynomials. In this module, we have introduced a very interesting interpolation method called cubic spline interpolation method, and we have mentioned that this method needs less computational time than other interpolation methods such as Newton's, Lagrange, Gaussian, etc. So, with respect to computational time, this method is efficient, but cubic spline method needs more space compared to the other interpolating methods. Due to the less computational time, the computer scientists are using this method, that means the cubic spline interpolation methods, in computer graphics, image processing, pattern matching and many other applications which are used in computer development.